This video is for the mean value theorem. The mean value theorem. So the mean value theorem states that if f of x is continuous in AB and differentiable in the open interval AB, then there exists a point C in the open interval AB such that f prime of C is equal to f of b minus f of a over b minus a for a less than c less than b. Okay, so what is this theorem meaning? It's meaning that for any closed interval AB, if f of x is continuous in this closed interval AB and is also differentiable in this open interval AB, then there should exist a C. There should exist a C in AB such that this happens. So what this is meaning is shown by this diagram. For an interval AB, there exists this C such that f of b minus f of a, this gradient of this secant, is equal to the gradient of the tangent. That is what it means. So whenever you want to prove something using the mean value theorem, you should first test if the function is continuous and differentiable in the respective intervals. That is the first thing you test. If that is true, then there should exist a C in AB such that f prime of C is equal to f of b minus f of a over b minus a for a less than c less than b. That is what we usually want to prove. So there is another case like when f of b is equal to 0, which is equal to f of a. So in this case where f of b and f of a are equal to 0, that this theorem is called the Rolle's theorem. So which is, for Rolle's theorem, you have to state that f of x is continuous in AB and differentiable in AB. Then f of b is equal to f of a, which is equal to 0. Then we'll be having if f of b is equal to 0 and f of a is equal to 0, then we'll be having f prime of c being equal to 0 as well. So that's the Rolle's theorem. Okay, so just for clarity's sake, we are going to consider an example which verifies the mean value theorem. Okay, so we're going to use mean value theorem to verify that to verify f of x, which is equal to square root of x minus 1 on 25. So to verify mean value theorem, we were given our f of x is square root of x minus 1. Right, so the first thing we need to do is to test whether let me just set the mean value theorem. So the mean value theorem that says that if f of x is continuous on AB and differentiable then there exists a C in AB such that f prime of c is equal to f of b minus f of a over b minus a. So that's the mean value theorem first. So we need to first prove that f of x is continuous. By nature of square root of x, you know that square root of x is actually continuous if x minus 1 is greater than or equal to 0. So we know that it should be continuous if for values of x which is greater than or equal to 0 under the square root. Since we know that under the square root you cannot have a negative if we are considering the real line as our base set. So this implies that x is greater than or equal to 1. So you can actually see that the interval we are considering is 2, 5, and 2, 5 is actually a subset of x is greater than or equal to 1. Therefore, f of x is continuous on 2, 5. Then for differentiability, we know that this function is differentiable in this range because this one is a positive x. So since we know that since f of x is differentiable they exist now a c in they should be exist a c in 2, 5. So in fact, like here we are supposed to prove that they exist a c. So here I'm gonna put required to prove because we are verifying the mean value theorem. So we are required to prove that they exist a c in 2, 5. That is what you are required to prove. So the existence is the one which you want to prove, the existence of that c. So what we do now is we apply this one. We say f prime, if we differentiate all right, so our f of x is equal to root of x minus 1, and f prime of x would be equal to 1 over 2 root of x minus 1. You can verify that one using those properties of differentiation. Then after this you can actually see that we are now saying f prime of c, which is equal to 1 over 2 root of c minus 1, is equal to f of a, which is equal to root of a is 2 and b is 5, which is f of 5 minus 1 minus root of 5 4 now 2 minus 1 over 5 minus 2, which is equal to 5 minus 1 is 4, so the square root will give us 2. 2 minus 1, this one will give us 2, then this one will give us 3. So it's actually giving us that 1 over 2 root of c minus 1 is equal to 1 over 3, which is 3 is equal to 2 root of c minus 1. Then we just square both sides. So 3 over 2 squared plus 1 is equal to c, which is 9 over 4. 4 plus 1. 9 over 4 plus 1 is just gives us what? That's 4 plus 9, that's 13. 13 over 4. So the next question we ask ourselves is this c in AB in 2, 5. So since we know that 13 over 4 is actually in the range 2, 5, we can conclude that we have verified the mean value on this function. So since c is an element of 2, 5, the mean value theorem is verified. Perfect. So the next example is show that if f of x is equal to tan x for 0 less than or equal to x less than or equal to k, whereas k is less than pi over 2, then tan k is greater than or equal to k. So what we need to prove is that tan k is greater than or equal to k. But for us to prove it, we have to first test if the mean value theorem works. So the first thing we do is we are given our f of x. The question we ask ourselves is f of x which is equal to tan of x continuous in the interval 0 to k. Is f of x which is equal to tan x continuous in 0 to k. Where k is less than pi over 2. So generally we know that the graph for tan, because we can just check here, the graph for tan, it looks like this. Where this one, it is asymptotical to pi over 2. So from 0 to pi over 2 to less than pi over 2, tan is continuous, right? So we have now, it's no longer a question. We are now saying f of x is continuous in 0 to k, where k is less than pi over 4, right? And then the next thing is f of x differentiable in 0 to k. Since we know that it's differentiable in 0 to where k is less than pi over 2, and it's actually equal to sec squared x, right? So let's now move forward. We actually managed to prove that it's continuous and it's differentiable in 0 to k. So the next stage now is to use mean value theorem. So which is Now, since we just want to prove this statement which we are given, tan a k is greater than or equal to k, we can assume that the mean value theorem holds on this one. So we are going to say that there exists a c in 0 to k such that f prime of c is equal to f of b minus f of a over b minus a. What is f prime of c? That's sec squared c. So you're saying sec squared c is equal to f of a. Our f of x is tan x. So you're saying tan of b. In this case, our b is if you check this in the form, our b is k and our a is 0. So tan of k minus tan of 0 over k minus 0. What does that mean? It means that tan of k is just tan of k. So just means sec squared c is equal to tan of k over k. But our worry now is how then do we now bound these, since we know that what we want to prove is bounded. You can see it. So our question is, how then do we bound it? How then do you bound these? As you can see, what you want to prove is actually independent of c and is bounded. So which is we need to get rid of this c by bounding it. So generally, we know that let's say sec x is generally equal to 1 over cos. So if we could find the bound for cos x, so cos x, but cos x is actually bounded by -1 and also cos squared now, because we want sec squared, so we want sec squared, cos squared. So cos squared x will be bounded by 1, and this lower limit will become 0 because it will be from 0 going up. So this means that if we divide both sides by cos squared, we get 1 is less than or equal to 1 over cos squared x. Right, that is what we get. Then after that, we're just going to replace sec squared with this inequality. So we have 1 is what is less than or equal to sec squared c, which is equal to tan k over k. And as a result, you can actually see that we can just multiply by k both sides so that we get k is less than or equal to tan k. And the proof is complete.